relations chapter was resonance. If you have any questions, you can let me know. So that's resonance part there. And yeah, that's about it. I want to start electric fields. Electric fields and magnetic fields. These are two very important topics. They have like a lot of breakdowns within them. So electric fields, what do we learn? So we learn about the uniform electric field. Then you have the non-uniform, which is one of those other parts of the chapter, and this is a separate topic. And then you have this small topic, which is called the capacitor. Okay, so these three all fall under electric fields. Therefore, we go to magnetic field. Magnetic field chapter, small topic. Okay, so this is a major hurdle we have. The chapters are small and not that complicated actually, but these are a little challenging. So yeah, we'll start with electric fields. Electric fields is very heavy on graphs. So the graphs usually cause a lot of trouble. Okay, so graphs but right. Anyways, so page 93. Okay, so this is page 93. Right. So what's an electric field? And as an Cambridge student, you know some of it from before because you had this in your O levels. So can anyone define what's an electric field? The same way you define what's a gravitational field, the same way you define what's a magnetic field. So gravitational field is a region in which a mass experiences force. What is an electric field? Okay, correct. Okay, so electric field hoche a region in which any charge experiences force. Okay, so region in which any charge experiences a force. See, electric field hoche a region in which any charge experiences force. I believe you guys have school exam on electric fields, right? 29, 28. Physics is on 28. Okay. So, problem clarify. Okay. So, region in which any charge experiences force, that's what your electric field is. So, what's an example of this? Example of, imagine you have a charge here, and it could be positive or negative. Both of them will experience force. So, you have a positive charge here. The region around this positive charge. So, a positive charge is a region, right? The influence of the positive charge is everywhere around this, a poor region like that. Okay, and just like gravitational field, everything is very similar here. So that's why the chapter is actually easy to learn compared to gravitational field because only is similar. The further you go away from here, as the distance increases, right? What happens to the strength of your field? It decreases. Okay, so this is the electric field, and as distance increases, strength decreases. As distance increases, strength decreases. Right, so that's how it is. But how do you visualize this thing? So we already have done this thing. First part of the chapter will take very little time because it's very similar to gravitational field. How do you represent a field? What do you do? Yeah, field lines, right? So you draw field lines. So we now need to learn how to draw electric field pattern, okay, or electric field lines. So this is your electric field representation. And it's just going to be the same as gravitational field. So what is this electric field representation? How do you draw the field around a charge? So on the chapter 2 obviously is based on uniform field, but we'll start with the non-uniform charge. We'll start with a unit point charge. So imagine you have this point charge here. Point charge assumption kora hoy. Does anyone remember what's a point charge or what's a point mass? What's a point mass or a point charge? So center of mass, center of gravity. So what is a point charge or a point mass? Acha, close. The answer is that it's a point, right? A region that doesn't have any dimension. There's no shape to it. So it's not a circle, it's not a sphere, it's just a location. And of course, it's the location that sub charge to থাকবে. So pointer হচ্ছে assumption. So what assumption we make here? This diagram that you're seeing here is for a point charge. And a point charge or a point mass assumption key, it does not have any dimension, which means that no size or shape. What's the consequence of that? That it does not have any dimension or shape or size? It means all the charge is concentrated at a point, as you guys mentioned, right? Which means all charge is concentrated at the point. So if you're given a point charge, how would you draw the field around it? So can you remind me what were the points to keep in mind for drawing gravitational field? Gravitational field ki chilo? Yeah, so the lines always leave the surface at what angle? 90 degree, right? Number one. Number two? Huh? Oh no, gravitational field is inwards, you're right. Electric field is different. The other one was that the lines can never cross each other. Okay, the field lines, they never cross each other. So whenever you draw a diagram, if field lines cross each other, it's a problem. So number one, they must leave the surface perpendicularly. Number two, the lines can cross each other. And there's one more. Parallel. It is. Yes. No, that's for uniform field, right? Yeah. So which way should the arrows point? Should they point towards the charge or away from the charge? Towards or away? It depends on the charge. Okay, so that's the biggest difference between gravitational field and electric field. Gravitational field, all the field lines always pointed which way? Inwards, right? Electric field, they can point inwards or outwards, depending on what charge, right? So then comes the question, which way do the lines point? So it turns out, electric field J region, right? It a line key represent for it. So let's write about the electric field line. So what's an electric field line? Electric field line definition হচ্ছে এটা ছিল O levels কারো মনে আছে what's an electric field line? It is the direction in which a unit positive charge moves in the field. Okay, so positive charge যেদিকে move করে, that's the direction of the arrow. Okay, it is the direction in which a unit positive charge moves in the field. So electric field line হচ্ছে the direction in which a unit positive charge moves in the field. So it's the direction of your positive charge movement. So can you tell me, carefully, if this is a positive charge, right, and I bring a positive charge in this region, let's say I bring another positive charge in this region, which way would this positive charge move? Will it move towards or away? Away, right? When I'm a positive charge, this charge is also positive, right? What does the positive charge do to the positive charge? Repel. So away. So if I want to draw my field lines here, the field lines should be pointed which way? Away. Okay. So another example of this would be this. This is, let's say, a positive charge. And this is a negative charge. Look at this carefully, okay? Positive charge, negative charge. And I have a field line here. Field line to the airport. For whatever reason, the field line looks like this, okay? We don't need to get into the reasoning behind why it looks like this. I have a question for you now. So the field line looks like this. Are you with me so far? It's a very random field line, right? What I'm going to do right now is place a charge here. It's going to be a positive charge. And positive, what each other? Repel each other. And positive, negative attracts. That you should know from, like, shorthand. So if I take my positive charge and place it here, like ekdometer pashe of it, okay? You need to tell me which way is the positive charge going to experience force right now. Is it going to be, it's an MCQ, is it going to be towards the negative? Is it going to be towards the positive? Is it going to be away from both positive and negative? Or is it going to be like that? So I have 4 options for you. So 1, 2, 3, 4. Which way do you think the positive charge will move at this moment? Yeah, which way does it move? Move is 4. So online, like everyone said 1. Which way would this positive charge move? So right now the positive charge is at this location, right? If I let go of it, it should move forward. There's a plus and a minus, right? There should be attraction and repulsion. Which way do you think will this move? 1. 4. Okay. So it was just written at the top. The electric field line also, the direction in which a unit positive charge moves in the field. Our field line to ekhane dawa, field line kotha theke kothaye jay? Plus theke minus, right? So that's the direction of my field line. Plus to minus, plus to minus. Very important. Regardless kothaye tomar positive charge ta rakha hocche, regardless of kon dike positive charge ta feel kortese force, the positive charge will always follow the what? The line. It will not go anywhere else. Okay, the line, like, essentially tells you what? The path that the charge takes. Okay, so whenever you see a field line that goes like this, it means that if I release a positive charge here, the positive charge would take that path. It doesn't matter kothaye plus, kothaye minus, kemne force hocche, it will follow that path. Okay, so yes, you might feel positive will get attracted by negative. It should go straight that way, right? But there's a positive also. What this positive? Repelling the positive. So it means that this one is applying a force that way, that is applying a force that way. So the movement is not going to be because of this or that. It's going to be the what of both, resultant. Okay. So eventually resultant will give you a path and we follow that path. Okay. Not what the direction looks like. Like one can't be the answer. Okay. It has to be this. So it's very easy to remember. If you want to know how your charges move, always follow the line. The line is where they move. Okay. So that's the path. So if I take all this information together and draw the field here, I think you guys should be able to figure that out. Lines will এরকম দেখতে হবে এই যে around a point charge. They're going to be equidistant. আচ্ছা 90 degree actually mandatory না আমি বুঝাচ্ছি. They'll be equidistant from each other, not in terms of length, in terms of angle, and the separation must be same. And that's about it. এখন তুমি যদি more lines add করো problem নাই. It's just that all the lines need to be what spacing? Equal spacing. Okay, given that this is a uniformly distributed charge, what does it mean by uniformly distributed charge? A uniformly distributed charge mane hocche, imagine you have a ball, right, and it's charged. Where is the charge? Everywhere equally. Okay, so there's no more charge on one side, less charge on the other side. It's equally charged from all directions. That's called uniformly charged. Okay, so আমাদের এখানে যদি uniform charge হয়, this is how it looks like. Now if I told you that this was a positive charge, right? If I told you this was a positive charge, can you tell me which way the lines point here? Towards or away? Away, right? Because I'm using a positive charge release kortam ekhane, wouldn't the positive charges move away because of repulsion? So the arrow should point away. If this was a negative charge, obviously the arrow should point inwards, right? That is it. And also you'll find something else which is true for gravitational field as well. The separation of the lines represent your what? Strength. Separation strength represent kore. So the further you go away, what's happening to the separation? Increases, which means what happens to the strength? Decreases. Okay, so yeah, that is what we need to know here. A type of field একটা নাম আছে, I think you know what is it? আজকে already বলছিলাম. What do you call this shape? Yes, it's called a radial field. Okay, so radial field is generated by a point charge. But point charge to assumption, to be honest, it's laziness from the part of the person doing the topic, because you're just assuming everything to be just a point. It makes your life easier, right? But that's not the reality. Reality, they're too different. Reality key, that the objects are not point charges. What do we do then? So we'll be doing that in a minute. But what to do when you have surfaces that are not a point, right? So imagine this. This is your surface. This is a negative charge. How would the field lines look here? So they'll leave the surface at what angle? 90. This is very important. Okay, point এটা দেখানো সম্ভব না, but এখানে দেখতে পারো. So they leave the surface at 90 degree, and because it's negative, right? Which way do you think the arrows will point? Yeah, towards. Okay, so point towards like that. So this is how a negative charge field would look like. আমাদের সবগুলো ড্র করতে হবে। তো তোমাদের এক্সামে র্যান্ডম ফিল দিতে পারে, বাট দেয় খালি দুইটাই, রেডিয়াল আর হচ্ছে ইউনিফর্ম, বাট আমি সবগুলো শিখে রাখি তোমাদেরকে। So yeah, this is how the field looks like. They must be equidistant and everything. Now let's try some examples. But before I get into examples, do you have any questions? So a very common definition that they ask you in the exam is, what are the field lines? So ignore for the issue. And এটার মধ্যে the answer is 4. So okay, a few points that you need to keep in mind when dealing with these fields. But তোমাদের question থাকলে আমাকে বলো, because I'm gonna ask you to draw some fields right now. Okay, so দেখো কোনো question থাকলে. So points to consider when drawing the field. One হচ্ছে the lines must not cross one another. They must leave the surface at 90. The lines must point from plus to minus. Separation of the lines represents the length. The lines must point from plus to minus. The direction arrow doesn't change. The lines must point. I think that's the arrows will be better. Strong to weak. Done. Okay, so couple of fields that need to draw. Examples. Okay. Draw the field pattern between two parallel plates. Draw the field pattern between two non-parallel plates. That should be it. This plate is connected to the positive terminal. Okay. And this plate here is connected to the negative terminal. Positive, negative. Yeah, draw the field pattern between these two. So to a positive plate here, by the way, do you guys know that when you connect a positive terminal to a particular metal plate, right, it also becomes positively charged? Cano. Tanmay, কি হবে answer? Answer বলো। কি হবে? এই যে এখানে হচ্ছে plate connected to a positive terminal, right? So what charge would this plate become? Why? আচ্ছা হ্যাঁ বলো কেন নেগেটিভ হবে শুনি। হ্যাঁ কানেক্টেড, তার জন্য ইলেকট্রন গুলো কি করবে? ইলেকট্রন গুলো কি প্লেট থেকে পজিটিভে চলে যাবে নাকি ইলেকট্রন গুলো হচ্ছে পজিটিভ থেকে প্লেটে ব্যাক করবে? কি হবে? Positive. Yeah, so it's a positive plate, right? No, sorry, neutral plate initially connected to a positive terminal. So what would the positive terminal do to the electrons? Attract them, right? So as the electrons are being attracted and taken away, what's left behind? Positive charges. So it becomes positively charged. Okay. So anyways, whenever you connect any terminal or plate to a terminal, it becomes that same charge because charges are taken away. Our negative cannot negative হয় because the electrons have been pushed onto the terminal. The neutral. The metal plates are generally neutral. Once you connect them to a power supply, they pull the electrons away or provide them electrons. Also, interesting fact: the higher the voltage you provide, the more they pull. So, high voltage will make them more positive. Strength, right? The first one is correct. The second one is not. Right. So those who are online, induction. Induction is the right term. You can use induction. Draw করে দেখো আমি একটু বুঝাচ্ছি জিনিসটা যে কেন টার্মিনাল গুলো প্লাস মাইনাস হয়। It's from your O levels, if you remember the induction process. Those who want to share your diagram can share it here. Yeah, so the idea is that these plates will become positively charged, and the reason why they become positively charged is because the electrons from these plates are attracted by the positive terminal, so they move away. You probably will also have seen this in chemistry, like when you connect electrodes to battery power supplies, right? Anode, cathode. Side, but how should the lines leave a surface? Add. No. আচ্ছা করে দিচ্ছি, ব্যাপার না। Little disappointed কারণ এগুলো O levels এ করছো তোমরা। like literally you guys. So far out it. But anyways, so what should the pattern be for this one? This is very straightforward. The field lines will travel from plus to minus, right? Erocom. Yes, you're right. And it'll be straight line like that. And these lines must be separated by what distance? Equal distance, right? Because this is considered to be a uniform electric field. So তোমাদের যদি এক্সামে বলে যে what's an uniform electric field, this is the diagram. Okay, this is uniform electric field. এটা নিয়ে আজকে আমরা শিখবো. We're going to do the math related to this. So this is called a uniform electric field. And the one at the bottom is yeah, so non-uniform. So problem হচ্ছে তোমরা এরকম যদি draw করো, it's an issue. And the reason behind that is there's an angle here, there's an angle here. These angles are not what angles? 90. So they must leave one of the plates at 90 degree and enter the other plate at 90 degree, right? How does that look like? Yeah, so যেরকম দেখতে হবে আর একটু subtle হবে, তোমাদের গুলো অনেক curve হয়েছে, some of you went like that, ওটাও কিন্তু অ্যাঙ্গেলটা extreme হয়ে যাচ্ছে, okay? So এরকম দেখতে হবে, where the angle here is how much? 90, and the angle there is also 90, and it should go from plus to minus, right? But the problem is, how do the field lines look like as you go there? Will it be evenly spaced? No. Ki hobe? Yeah, they'll start to get closer and closer. And why is that so? Yeah, because when the plates get closer, the charges experience more force, right? Because the distance is less. So as a result, it gets stronger as you start to move closer to the terminals there. Okay. That's how it is. So this one here is referred as a uniform electric field. And the one at the bottom is a non-uniform electric field. So uniform lines would come out from positive negative lines and go further apart as they bend in the middle and leave 90 degrees. Yes, that's true. What are the features of a uniform electric field? The lines must be what to each other? Parallel. And what else? Equally spaced. Okay, because অনেক সময় ভাবে যে parallel হলে হচ্ছে, but that's not enough actually. Because you may also have something that looks like this, where lines will এরকম দেখতে. Is this uniform field? No, right? Why not? Because it's very weak here, and it's very strong there. Though the lines are what to each other? Parallel. Okay, so that's not the one. Clear? Question তোমাকে বলতে পারো. So yeah, that's how we represent field. এখন এরপর আমরা হচ্ছে field measurements এ যাচ্ছি. So one more time before I move on, what's an electric field? It's a region in which charge experiences force. Any charge is fine. And what's a point charge? It's a charge that has no dimension, basically a single point. The mathematical definition of a point is a shape with no size. Okay, so there's no dimension to it. The field around a point charge looks radial, where you'll find that the angles are equal. And the further you go away, the strength decreases. We'll see that mathematically. You've already seen that in the gravitational field chapter. It follows a what law? The strength and distance. Inverse square law. Okay, inverse square law means as the distance increases, the strength decreases by a square factor. Our field lines always point from plus to minus. Regardless of how your charge is pointing at the moment, it will always take the path of the line. That's important, okay? And these are the points that you need to keep in mind when drawing them. This is how a uniform field looks like. This is how a non-uniform field looks like. In the second field, the field loses strength, correct? So if you go this way, this region here is actually strong. It's like a strong region, and it's weak on the other side. So it's like that. So it weakens as you go because not only that, they're not parallel, they're not equidistant, and the distance and the spacing is what matters. Okay, so you'll find that the distance here is like really small, and that's the very large spacing, right? So this is weaker here. Okay, so let's move on. Can anyone define to me what is a gravitational field strength? Definition of gravitational field strength. তোমাদের রিটেনশন কি less than 100 days 100 days আগে করছিলাম আমরা এটা, তারপরে কি ভুলে যাও সবকিছু তোমরা? What's the gravitational field strength? Something per unit mass. Field strength. G, the small g. আচ্ছা ফর্মুলা বলো দেখি, at least something. ঠিক আছে, that's correct. So yeah, gravitational field strength definition হচ্ছে it's the amount of force exerted per unit mass in a gravitational field. You said mass and field, আর কিছু বলো নাই. So yeah, that's gravitational field strength. So what is electric field strength along that line? Electric field strength is the amount of force experienced by a unit point charge, positive, negative, doesn't matter, in a what field? Electric field. Okay, so gravitational field strength is generic formula ki chilo. I know you guys told me the like actual formula that G equals to gm by d square, but what's the O-level grade 9 formula? F by, yes, G equals to F by m, force per unit mass, right? So electric field strength, the generic formula ki hobe. I don't want to like make it different. I want to show you similarity so that's easy to remember, right? So what's the formula for electric field strength going to be? Yes, force by charge. Okay, because gravitational field strength is the force per unit mass. Electric field strength must be force per unit charge. And gravitational field strength, the symbol is small g. Electric field strength, the symbol is capital E. So we can't use energy jono E anymore. I think I talked about this before. It's either W or Q. W in work done, Q in heat, right? E is not allowed anymore. So E is for what? Electric field strength. Okay. So electric field strength is F by Q. This is the equation. Definition of the energy. So what's electric field strength? Is the amount of force exerted per unit. Positive charge to that. Some of the data, but it's actually true for anything. Right. So electric field strength is the amount of force exerted per unit positive charge in an electric field. Once again, it's E equals to F divided by Q. Capital Q, small q doesn't really make a difference. এখানে E হচ্ছে electric field strength. What's the unit for electric field strength? Newton per coulomb. F is Newton. Q is coulomb. Very straightforward. So এটা use করে we will now build on our chapter. So our first task this is like background work. We haven't started the chapter ওরকম ভাবে. So we'll first start with the uniform electric field. Their properties, what it means, how does it interact with distance, and then we'll do non-uniform electric field. So yeah, E equals to F by Q. Oh, so that's a good question. Why are all the definitions based on a positive charge? Negative charge is like electric field experience for a force, right? So does anyone know why is it for positive charge only? It's a thing we have talked about, or at least must have been discussed at some stage. What? Convention. What's the convention based on? Why did they decide to do this? Nuclear mass. Oh, proton is heavy charge, no? Achamboli, the reason behind this positive charge, it's actually a complicated answer, but I'll try to simplify it. So you know that the discovery of electricity, right, happened like 1700s, and that's like Benjamin Franklin with the like kite and everything, right? So he discovered there's something called electricity. It transfers energy, right? Lightning can cause fire, right? There must be some energy out there, and then people started to generate that on their own using friction, and there are devices that do that. Eventually, Volta, there's a person who made a battery out of it that he can actually produce, electricity by storage of something, chemical reaction, right? But this is a time when we still didn't know what an atom was. Atom ki kyun jana, but we still know that there's charge, there's something moving around. So they started to make assumptions, and they assume that there's something actually flowing through the material, and they assume that thing to be what charge? Positive. Because they have no clue, so they just call it that there's something moving through here. We'll call it the charge, and we'll call it the positive charge, right? And eventually they realize that there's an opposite to it. And what is that? Negative. Because they found that the positive repel, but the positive negative keep or attract for it. And this is like mid 1700s, 1800s. Atom discovered John Dalton just came up with the word atom, and no proof of anything, right? Eventually, in 1900s, we discovered this person J.J. Thomson. He came up with the existence of protons and electrons. And that's when we realized that there are protons and electrons, plus and minus. But that's when we also realized protons don't flow, protons don't move. What moves only? Electrons, right? It's been almost 150 years of advancement in electricity, after which you realize that electrons are actually moving, not the protons, right? But then they realize something. It doesn't change their math, because ওরা plus জায়গায় minus use করতেছে. It doesn't change the fact that there's an electric field out there, there's a force out there. So they decided that there's already advancement and everything is working. By the way, the people who are doing these stuff, right, they were doing it under a lamp running on electricity, which means electricity actually works and their formulas actually work, right? But they didn't know electrons were responsible. So they decided in 1900s at a convention where they said that we'll consider the charge that flows to be positive, and we'll only deal with positive charges for math. And it made our life easy. You know why? Because if you only have positive charges, you don't need to worry about what negative will do. Because you just do your math assuming everything is positive. If it happens to be negative, what would you just do to the answer? Reverse it. Okay, so if it goes left, it goes right. If it attracts, it repels. That's it. Our difference nine. So to keep things simple, they have assumed that everything, every equation, everything that we do will be based on the assumption that what charge only exists, a positive charge. Okay, and that's the convention, and that's a taste of it you get in your O-level electricity. That current flows from what terminal to what terminal, plus to minus. But current actually flows negative to positive. Conventional current also plus to minus. So এটার জন্যই definition মধ্যে positive charge টা রাখা হয়. So yes, when we do our math, we will always assume what charge do we have? A positive charge. Or if it's a negative charge, you just reverse your answer. Okay, so let's move on. Can you go to page 96? Uniform electric fields. So let's start. Page 96. Okay, shall I screen it? It takes 5 minutes to explain this whole idea, but the work behind it can go on for much longer. So let's first start. So how do you generate a uniform electric field? So I want an electric field and I want it to be uniform, right? So the way we do this is we take plates, metal plates, and we place them parallel to each other like that. And then we connect these plates to terminals, like battery terminals. Now, it could be connected to a positive terminal. It could be connected to a negative terminal. It could also be connected to positive, and you'd still have an electric field. How is that possible? This is possible if your positive field or positive terminal and the other positive terminal have different magnitude. Magnitude of what? Voltage. So এটা যদি plus 1000 volts হয়, আর এটা যদি plus 1000 volts হয়, there is no electric field in between. Cannot, because is there any net force exerted here? No, because it's a 1000, it's a 1000, right? But the moment I make this, let's say, uparata, I make this 4000, we suddenly have a watt here. electric field. So what is the main requirement for an electric field? A plus charge, a minus charge, or a net charge? Net charge. Okay, so তার জন্য এখানে দেখো in the diagram I've provided here, I've provided a lot of positive charge here, 1000, right? I've also provided a lot of positive charge on the bottom as well, yet there's no net effect, because they're equal and opposite, right? So if you want to have a net effect, you need to have a net charge. So this is fine. So plus and fine, plus and minus are fine. In fact, এটাও fine. যদি এটা 1000 না হয়ে কি হতো ভ্যালুটা? 0. Completely fine. Why 0 and 4000 কি difference আছে না একটা? So it's possible. So the main idea is that you need to have potential difference for a field to be generated. So potential difference যেভাবে আনতে পারো তোমরা. So anyways, for simplicity purpose, I'll keep it as negative here. So there's a field generated in between. Okay. This field that's generated here is considered to be a what field? A uniform field. Why is that so? Because the charges are uniformly distributed. So to carefully দেখো কি করব আমি এখানে I'm going to draw the charges here, and when I put my charges on this particular plate, right, the charges will uniformly distribute. Do you understand why? Now imagine charge flow করতেছে, right, from a pipe থেকে ধর charge আসলো and the charge flows here. Do you think the charges will accumulate at one place, or do you think the charges will spread out and even out? Why? Why do you think that the charges will even out? Yes, and they take up space to minimize repulsion. Do you know this? That there's this idea out there that charges, when they're let to go freely, right, they'll move around until they minimize the what between them, repulsion. And that means that they have to spread out as far as possible and as evenly as possible. And as a result, they'll spread out perfectly evenly distributed out there. So an example of this would be, imagine I take some spheres, এরকম sphere নিয়ে এগুলা charge, এগুলাকে throw করলাম on a table, right? If they're electrons, right, what would the spheres do to each other? Repel, and they'll start to move around. And they'll move around, and eventually they'll take up a space and a setting and a arrangement where the repulsion between them is what? Evenly distributed and equally distributed, which means that no one is actually getting a net force. And as a result, they'll stay there, okay? It's a very important concept in chemistry, bonds. I don't know if you learned this or not. The chemists say, have you learned bond angle maximization? Why does that happen? Yeah, to minimize the repulsion as possible out there. And there's a chemical out there, not a chemical, a structure, C60. Do you know what that is? Yeah, Buckminster Fullerenes. It's basically a structure of 60 carbon atoms. ওইটার repulsion কমাতে গিয়ে, what structure does it become? A ball. And it's the most effective shape out there. The point I'm trying to make here is that whenever you release charges, what will they naturally do? They'll evenly spread out. And as they evenly spread out, it will eventually lead to a what kind of field here? A uniform field. Now here is a disclaimer, unless or otherwise stated. অনেক সময় exam বলবে that there's more charge here. Telling into the answer and the math is different. Yeah, good question. Why would that happen? The material on which the charges are moving doesn't have the same amount of conductivity. So imagine one side is a little more conducting than the other, right? Charges will prefer that location. Right, so what happens here is that your charges will evenly distribute here. And let's cut to the chase. What will happen to the field between my nature field uniform, right? And how does that look like in terms of diagram? The field lines will travel from plus to minus. They will all be what? Spacing from each other, equally spaced, right? And that's it. So the diagram for uniform field will look something like this. We have just done this like 5 minutes back. Okay, so that's the official version of it. Now, what does it mean if my lines look like this? Do you see how the lines are separated? What does it mean? This versus that. How do they differ? Right. So যেটা হচ্ছে যে তুমি যদি ভোল্টেজটা এখানে উপরে 4000 আর নিচে -1000, right? What's the difference? উপরে 4000, নিচে -1000. What's the difference? 5000, right? If I made this 10,000 in your diagram, you'd end up with how many lines? double the number of lines. Okay, so the number of lines actually mean what? The strength of your field. Okay, having more number of lines would mean what? Stronger field, obviously, right? Now a diagram অনেক সময় কিছু বইতে also I've seen in school স্কুলে করায় is যে এরকম একটা পাশে লাইন ড্র করে which is curve থাকে কেন curve হয় এটা আমরা normally use করি না but just letting you know that sometimes they'll draw a line on the side that looks curved like that. What does that mean? Very good. আচ্ছা, so আমি একটা diagram দেখি একটা. So তোমার field হচ্ছে আমরা assume করি it's a 2-dimension structure and everything, right? But the reality is it's not 2-dimension, it's 3-dimension. How is it 3-dimension? Let me show you. So when you বুঝছো the plate is thick, right? So doesn't the plate have like a side and wooden field lines leave the side as well? So this is what it looks like. হ্যাঁ এই যে মানে উপর থেকে নিচে না এই যে এরকম আসবে so do you see যে সাইড থেকে বের হচ্ছে এই যে এই সাইড থেকে বের হয়ে আবার সাইডে ব্যাক করতেছে তার জন্য কার্ভটা দেখা যায় like that they'll have to go over their lines, they can't cross their lines, so এটা হয় না ম্যাগনেটিক হয় না ম্যাগনেটিক তো এগুলা এদিকে চলে যাবে আর এখান থেকে এদিকে আসছে. So yeah, this is your uniform electric field. What are the features? I mean, both this in a minute. But is there anything that you need me to clarify? Now, how do we find the strength here? So look at this. I'll be doing something very important right now, so listen very carefully. Let's say I place a charge here, and আমরা যখনই charge place করব in physics, or তোমাদের syllabus at least, we will always assume this to be a positive charge. There's a name for it. It's called a positive test charge. What is the positive test charge? So if I want to, find out what strength the field has, right? We drop a charge there and we see what the charge does. But whenever we drop a charge out there, what type of charge do we drop? Positive. It's always a positive charge, okay? Negative the kori na. Somebody like a positive test charge you can drop kori, right? What's your logic telling you? This positive charge here, right? What will it do? Will it stay there or will it go the other way? Can you give me reasons why? Yes, good. Yes, that's why I said reasons, because there are two things that are happening here. One is the upper plate will repel my positive charge, and the other one is what? My lower plate will attract the positive charge, right? As a result, this will experience what here? Force. And this force is acting over a charge, right? Wouldn't that mean that there's an electric field out there? Now, as this positive charge moves, okay, a positive charge to move for this. What do you think happens to the force? Remain same. Why? Right, good. So you're saying that this will be a little less because it's further away, and this will be a little more because it's closer, right? Okay. And as the charge ends up here, what will happen? Yeah, so this will be much larger, and this will be almost non-existent. যেমন এখানে এটা যদি non-existent consider করি, এটাকে এটা consider করি. তোমরা কি বুঝছো কি হচ্ছে এখানে? So as you keep going further away, let me draw a graph. It'll be easy that way. So you look at this graph. This is the graph for force versus distance, and distance is the distance between the plates. Okay, the force, red color j arrow is what value here? Minimal. And what value here? Maximum, right? So as I start to go away, the red arrow increases, but simultaneously what happens to the blue arrow? Decreases, right? At any given point, if you actually add the two values, you'll find that what do you get? A constant value. And that's the reason why we call this a what field? A uniform field, because regardless of how the forces interact, the net force acting on the charge at any given point is always the what? Same. And that's the uniform field. So uniform field ki hocche to shunne nao carefully. Wherever your charge is, right? What force does it experience? The same force. There's no change. Ekhane ja force, ekhane same force, ekhane same force. It's all the same force everywhere. Do you know an example of where this happens? That the force is the same all the time everywhere on an object? Surface of Earth, and what is the object that experiences that force? A mass, right? So একটা mass যদি Earth's surface right now, if I take this remote here, right? It force আমি যেভাবে move করি, isn't the force the same, the weight? Why am I saying this? I'll explain right now. It means that তোমাদের এই chapter you can get questions from projectiles. You have projectiles in your AT. Okay, projectile motion মনে আছে? So এখানে if I throw a charge like this, do you think the charge will go straight? No, because what's action on the charge? The downward force. So there's a forward velocity and a downward force, right? What would that make the charge do? Parabola. So the questions they'll ask you is like find the path of the charge in the field. Okay, it's a very common theme that we have. It ignores the magnetic field of type. Okay, so you need to know projectiles, at least have recollection of it. Okay. Components like horizontal to fixed or just vertical to the math. So yeah, that's your field. I'm going to take you notes which you copy, you know, especially why is the force the same? Capacitors after electric field. You have it in your exam, right? Yeah, I'll take a class on it, but your exam syllabus is everything till electric fields. The gravitational fields, thermal physics. Oh, magnetic field as well. Entire electric field and capacitors. Achha. So electric field, I think your exam is next week. Yeah, so before that, maybe I'll be done with 70% of electric field. Capacitors, I'll take an extra class on it because I don't think I'll be done by that time. Okay. Also in the extra class, you can do some questions from previous chapters and share with me or whatever problems you have from the previous topic. I think you have all solutions. Can the test charge be negative? No. Test charge is always positive. One day. Which chapter? It's something that all schools are doing. I'm not really sure if it's helpful. Because that's not how it normally used to be. But now I see like schools, they do chapter half an hour and then question paper 2 hours. And then chapter half an hour, question paper. It's supposed to be the other way around, actually. You're supposed to give more effort in understanding the topic and then solve questions later on. Because eventually you will be doing question papers. So I don't know, it's something they do. Yeah. I'm sure your classes uses projectors, right? Oh yeah, I have found that like the year these started, like plastic projectors and these digital things, right? Teachers don't need to write anything. They'll just do slide. Oh, yeah. I mean, yeah, I know because I've never seen this, but last 3 years after 2020, it's been a new thing. Like they just show slides in one class. Also, the chapter is done. You can see the slides later on at home. Let's do question paper. But yeah, I don't think it's working. Which I think is better than a slide, especially if it's a YouTube class of somebody else. Udemy. Udemy doesn't take physics. I have thought about this. Like, no. I've tried this in back in 2020 when we had online classes only. I thought like I'll just take all the recorded classes and upload it in Udemy because I didn't have like a platform for it, and they said that they won't allow educational classes. There's this another page that's brilliant. No, 10 minutes is brilliant. Brilliant is another platform. They allow physics, but they said that the videos should be less than 5 minutes, like very small videos. Eh? Right, so this is the uniform electric field. Next, first I'll show you the equations of it. There's a derivation as well, and then we'll start doing the questions. Chapter 22, uniform electric field.
So funny.
So funny. Yeah, it is actually easy. The non-uniform is the problem. How does the potential difference affect the strength of the field line? So the greater the potential difference, the more the force the charges experience. As a result, the strength increases. We will see a formula soon. The formula tells you how they're linked. So electric field strength is directly proportional to the potential difference. Key examiner? Oh, yeah. Even for weight. Yeah.